Do you see the screen, right?
Yes, doctor.
Okay, good. So we'll start a new topic, which is about the, now we will move to sequential circuits. So far we did, combinatorial circuits with different components that we can use, even the others, half adder, full adder, we use them as well in combinatorial circuits. So starting from this topic, it's sequential circuit. Of course, the first thing that we need to do is to talk about the components that we use in sequential circuits, which are the latches and flip-flops. And then, as we did with combinatorial circuit, we did VHDL and we showed you how to, to design or to describe combinatorial circuits using VHDL. We will do the same as well. We'll show you how do we use first those components to build sequential circuits, and how do we describe the circuit that includes those components using VHDL. Right. Of course, those components, they come as well in chips, like the normal gates. So you can find them as well in chips. So and you can buy them and use them on a breadboard or a PCB. So we'll talk about we have different types of latches and flip-flops. So we'll talk about each one. So what is the function of each one? So for example, we have different gates. We have AND, we have OR. So AND and OR are the functions. But they are all two input gates. So we have two input gates with one output, but it depends on the functions, how the relation, which defines the relationship between the input and the output, or the output and input. So we have as well different types here for latches and flip-flops. So I will talk about those types. So we have the SR function, we have the D type function or delay function, and we have JK function. And the JK function we found is only in flip-flops. This is why I put JK flip-flop. So the JK function. And we'll talk about this with more detail. So we'll talk about all different types of latches and flip-flops. And then those last 2 points will show you how to use them, for example, to build simple circuits. And of course, we will do more, but those are just some examples here. We will finish with them to show them how we can use these components. Right. So as I said, the latches and flip-flops are the main components in sequential circuits. So they are components which they have inputs, they have outputs. Now you need to know what's the difference between the. You will see that they have two outputs. These latches and flip-flops, and they have the inputs will depend on, of course, which function we have. So we may have 3 inputs, we may have 2 inputs, and so on. So we'll talk about this as well. And then the outputs, this output will depend on the inputs and the history of the output. So what was the output before? So at this time, t is equal to t0, we have the output. At t is equal to t1, the new output will depend on this previous output as well, plus the inputs. So this makes the difference between the combinatorial components. For components, combinatorial, we don't care about what was the inputs before. We don't care. Oh, sorry, the outputs before. We don't care. We just have value 0, 0. We just update 0, 1, 0, 1, 0, 1, 1, and then we get an output. We don't care what was the output before. So this is the main difference between these components and the components that we use in combinatorial circuit. So we have, as I said, we have latches and we have flip-flops. Of course, there is a difference between them, so we'll talk about both of them. Latches, as I put here, the output assume their logic, or we will get an output almost at the instant that the input changes state. This is very close to the combinatorial, so it's almost at the same time, but there is always a delay. And in some, we have what we call gated latches. They have an input that will control the output as well, that will have more control on the output. So we have other inputs, but this gated latches, they have what we call the enable input, which if this is 0, the output will not change. Regardless of what we have on the other inputs, there will be no change. So this needs to be 1 to get an output, to update the output. So we have latches, normal latches. We have gated latches. So the gated latches, they have an extra input compared to the latches. So we have one extra input, which is the enable input. This is why we call them gated latches. So it will depend on input can be gated with an enable input. So, and this enable input, it's extra. And then we have flip-flops. So we just use FF, flip-flops or FF. I will write FF for flip-flops. Flip-flops, they have as well inputs, they have outputs, but they have one very specific input that is, one input which is very specific or very special, which is we call it clock. And this is a special square wave input. So it's a square wave. What does it mean, square wave? It's like this, 0, 1, 0, 1, 0, 1. So it's continuous. So it's an input that is always like that, 0, 1, 0, 1, 0, 1. And of course, this will depend the time. So this could be 10 milliseconds, this could be 20. And we say this is the frequency of the clock. You know what is the frequency or the period of the clock. So this can change, but it's always the same shape. It's always a square, 0, 1, 0, 1, 0, 1. This is what this input. The other inputs, they can change depending on what you want to do, but this one is always like that, constant. And then this will control the output. When it will control basically when do we need to update the output, or when the flip-flop will get its output updated. So it controls. This is why we say the output is updated in synchrony with this signal or this special input. Of course, as you can see here, we have this signal, or for this input, we have 0, and then we go to 1. This time, when we go from 0 to 1, we call it the rising edge, going from 0 to 1. And here, going from 1 to 0, call it the falling edge. Yeah. So we have rising edges and we have falling edges. So the output, it depends on the flip-flop that you want to use or that you choose. So you can get flip-flop that will work with rising edges. You can get a flip-flop that will work with falling edges, or you can get a flip-flop that will work with both. And in this case, we call it pulse triggered. And I will explain this further with examples later on. So what I want you to understand now is that we have latches, we have gated latches, and we have flip-flops. The flip-flops, they have what we call a clock, plus other inputs. Yeah, it's not just a clock. There are other inputs, and the other inputs will depend on the function. We have SR, we have D type, and we have JK. So this will depend on the function. And then the output will be updated, of course, based on all inputs, but with more control of some specific inputs. For example, for the flip-flop, we have the clock, and for the gated latch, we have the enable input. And for the normal latches, it's just the other input, so it's controlled by the other input. Or it will depend on, the output will depend on the other inputs. So we have, as I said, three functions or three types. we have 3 components, and for each component, we may have different types. So we have latches, we have gated latches, those are the components, and we have flip-flops. And for each one, we may have different types as well. So for example, we have the SR function. So I can find, if you go in the market, you can find SR latches. You can go and buy an SR latch. You can go and buy an SR gated latch. You can go and buy an SR flip-flop. So with SR function, we can find it with all types, with latches, with gated latches, with flip-flops. And this is what I put here in this table. Now, D-type, we don't have a D-type latch, but we have D. We don't put type, we just use D. D-gated latch. And we can find D flip-flop. So you can go to the market, you will find this. So we have D gated latch, we have D flip-flop. And then for JK, we find it only as a flip-flop. So there is no JK latch, there is no JK gated latch. So we find it as just JK flip-flop. So in total, we can have 1, 2, 3, 4, 5, 6 different types or different components. Is this clear so far? Now I'm going to talk about the functions themselves and what do we mean by each function? What do we mean by SR, D, and JK? So I will start with the SR function. I don't know, do you remember this circuit? We used it in the components to explain components when we display those XOR gates. So the SR function, and by the way, for all those components, we will have two outputs, as I said, Q, and the other one we call it Q bar. So one is the opposite of the other. So if you guess this output 0, this definitely will be 1. If you guess this output 1, this definitely has to be 0. So one is the opposite of the other. So all those components that I mentioned here, they all have two outputs. One is the opposite of the other. Now the difference will be in the inputs and the function itself. Now if we say SR function, so if we look for SR latch, if you look for SR latch, you will definitely have two inputs called SR. And if you work for SR, this is SR latch, SR, for example, gated latch, you will have an extra input, which is the enable. This is the gated latch. Now, what is SR? So I will explain first the SR function, and then how do we find it in the latch, in the gated latch, and the flip-flop. So SR is basically, we have those are the two main inputs, and this is how it works. So if the S is 0 and R is 0, I don't know, this is very strange, you know, this should be QN here. This is SR, so it's a reset, 0. This is a set, and this is this is very bad, huh? It changes the PDF is correct. Well, if you have the PDF in front of you, you can see that this is correct. So this is not allowed. 1 is not allowed. So why? If you put 1 here, you will get Q1 and you will get Q bar 1. Or you get both of them 0, sorry. If you put 1, you will get this 0 and this 0, and this is not allowed. I mean, you are not supposed to have the same output, the same value. One should be the opposite, and this is what we mean by a latch. And this is set, this is reset, and this is no change. So basically, what do we mean by no change? If we put 0, 0, here I just put Qn plus 1, which means the next Qn plus 1 means next Qn. What will be next Q? The next value for Q. Qn is the current value. So now if we have, let's say if we have Q is 0. At this time, Q is 0. So we'll have 0 here. 0. This means this will be 1. In this truth table, I just put Q. Of course, there is no need to put Q bar because it will be the opposite. And you will see in always I will talk about Q, but you should know that the other output is exactly the opposite of the Q, and that's it. So if Q is 0 now at this time T0 is equal Q, at time is equal T0, Q is equal 0. Now next, at time T is equal 1, we will put 0, 0 here. What will happen? Even if you work with this circuit, you will get Q0. So it will stay as the previous value, which is 0. So it will not change. This is what we mean by Qn here. Qn plus 1 will be equal to Qn, to this, the previous one, or the current one. So the next one, Q, if I put here Q0, here I put Q1, will be equal to Q0, which is equal to 0. Do you understand what we mean by Qn plus 1 and Qn? So it means that the current value. So what will be the next value if we put 0, 0 on S and R? What we mean here, it will not change, no change. So it will stay, if it was 1, stays 1, if it was 0, stays 0. And then if we do 0, 1, SR. So S stands for set, R stands for reset. And you know, when we reset something, when we say reset, it means we put it to 0. If we said set, we put it to 1. So set is we put to 1, reset is we put to 0. And that's it. So this is what we are doing. So if we have S is 0 and R is 1, then you get 0. So you are resetting. This is a reset. Q is 0. So it doesn't, regardless of what was the previous Q, it will be set, a reset to 0. 1, 0 is a set. So regardless of its previous value, it will be, we set it to 1. We force it to 1. And then 1, 1, of course, we cannot set and reset at the same time. So, and even if you put 1, 1 here, you will get 0, 1 or 0, 0. And this is wrong. This defeats the purpose of having Q and Q bar. And you will see later why we need Q and Q bar. So we have two, and you can use both of them in a circuit. We will do it in the next lectures. Yeah, not today, but in the next lecture. But for now, you need to understand that we have two outputs, Q and Q bar. One is the opposite of the other. And then now this is the SR function. This is how it works. Is this clear? Is this clear so far? Are you connected? When I ask questions and I don't hear anything.
Clear, doctor.
Yeah. Okay. So this is for the SR function. Those are the symbols for the the component. So this is an SR latch, for example. So we just use a square and we put SR Q bar. This is the gated latch. So we have, in addition to SR, we have this enable. And for flip-flop, in addition to the SR, of course, Q and Q bar is always there. We have what we call the clock. I told you for flip-flops, we have clock. And the clock is a square wave or square signal. 0, 1, 0, 1, 0, 1, continuous. Now, how does it work for the gated latch? So the SR function, you know it. Now, if for the gated latch, if enable is equal 1, then it works as I was explaining here. So wherever we put values on S and R, things will change. Is this clear? So if enable is 1, then Q and Q bar will be updated according to S and R. If enable is 0, then it's no change. So if Q was 0, it stays 0, and until this enable will change to 1. So there will be no change on the output. If Q was 0, it will stay 0. Is this clear? For the flip-flop, we have the clock. And I will explain this later in the, I think in this slide here. So I'll explain how do we work with the clock. So again, R will depend on S and R, but they will be updated like here. Q and Q bar will be updated only if enable is 1. If it is not 1, there will be no change on the output. Even if we change S and R, Q bar will not change. They will stay as they were. Same for SR flip-flop. Q and Q bar will be updated based on the clock signal. I mean, when do they need to be updated? It will be based on this clock. And then I will explain this later, yeah? Right. That's very bad. I don't know why this has changed completely now. Let me change to the, probably PDF is better. I don't have to... it was lecture 9, right? Yeah. I'll just work with PDF. So we stopped here. We said the for clock, I will explain it later. How does it work? Again, Q and Q bar will depend on S and R, as I explained here in this table. The question is, when do we get this to be updated? When do we update Q? So it's not only when we change S and R, but we need to observe as well this clock. And that's what I will explain later, yeah, after this slide. I think it's after those 2 slides. Right. Now we'll go to the function, D function. D function is simpler than the SR. It's much simpler. And for D function, as I said, we have we can find D or gated D latch, and we can find D flip-flop. So those are the 2 possible values that we can possible components that we can find with D function. So for D, you will see that we will have one input called D. We will have the 2 outputs, Q and Q bar, sorry. So Q and Q bar are always there. Plus, if this is a flip-flop, we will have what we call the clock. And if you have noticed in the previous, we just put this small symbol here to indicate that this is the clock. So even if we don't put the name here, you should know that this is a clock, CLK. So we use this this notation here, or this symbol here, like triangle, to say that this is the clock. I did it here. Do you see it here? So even if you don't put the name, you should know that this is the clock. Right. So how does it work, the flip-flop? Or what is the Q based on D? So D flip-flop, you can say that Q follows D. Whatever the value of D, you will get Q equal to D. And that's it. So do you see here, if D is 0, Qn plus 1 is 0. If D is 0, Qn plus 1 is 0, regardless of what was the Qn, the previous Q or the current Q. If the current Q is 0 and D is 0, it will stay 0. if the current Q is 1 and then D is 0, now the next value for Q, it will be 0. So Q follows D, as simple as that. So Q is equal to D. If Q is 1, we get Q bar, or Qn plus 1 is 1. And that's it. I think this is very simple. If you have an SR latch, and this of course applies to the gated latch and to the flip-flop. So this is flip-flop, and for gated latch, we will have D, we will have enable, and then we will have Q and Q bar. So this is for D gated latch, and this is for D flip-flop. You can build a D flip-flop, or sorry, if you have an SR latch, you can build a D type latch or gated latch. Of course, we need enable here. Yeah, we don't have the. So, for example, here, as you can see, based on by just connecting an inverter here, by taking this D and connecting inverter, and you feed it to R. So if D is 0 here, what do we get here? We get 0 and we get 1 here. So this is a reset, right? SR. If R is 1, it's a reset. So we'll get Q0. If D is 1, so I put it in green. So if D is 1, I will get 1 here and I will get 0 here. So 1 is a set. So we'll get 1. So as you can see, Q is always equal to D. So if I have an SR latch, basically I will have the two functions, set and reset only. I will not have the other one, because this will force only two possible cases, 0, 1 or 1, 0. So I can build an SR latch, sorry, a D gated latch using an SR gated latch. This is the symbols for both of them, as I showed you here. I already showed you this here. So this is a D-type gated latch, and this is a D-type flip-flop. So for the gated latch, we have enable. For the flip-flop, we have clock. Right, now I'll show you the clock. Now if I take the case of a D flip-flop, we said that the D flip-flop of all flip-flops, they have clocks, and the clock signal is a simple square wave, 0, 1, 0, 1, 0, 1, 0, 1. And then I said that in this wave, we have this is a rising edge. So when the signal goes from 0 to 1, we call this a rising edge. When the signal goes from 1 to 0, this one, for example, here, we have a falling edge. So we have many rising edges and we have many falling edges. And then if you go to the market and you want to buy a D flip-flop, you can find D flip-flops that works with the rising edge. You can find flip-flops that work with the falling edge. And in this case, we call them, they are edge triggered. So the output will be updated depending on one of the edges. Or we can have what we call, which I will cover next, pulse triggered. It will depend on both. And this information, you will find it in the data sheet of the component. So when you go and buy, it will explain clearly, is it positive? And by the way, rising edge and falling edge, we use positive and negative as well. So we can say positive edge triggered or negative edge triggered, or falling edge triggered or rising edge triggered. So they are the same. So positive, rising and positive is the same. Falling and negative is the same. Right. Now, you know what is D, so you know how does it work. So we say that Q is equal to D. Right? For the flip-flop. Now we need to consider the clock, because it's another input and needs to be considered. If this flip-flop is positive edge triggered, This means it operates on the rising edges. What does it mean, operates on the rising edges? This means the output will be updated when we have a positive edge trigger at this time. So the output will be updated here, and it will be updated here, and it will be updated here, and it will be updated here, and then here. In between, there will be no change. The output will not update it. And of course, it will be updated based on the value of D. So here, as you can see, if we have a falling edge, no change. If Qn plus 1, it will be equal to the current Q. There is no change. There is no change here. There will be a change if there is a positive edge trigger. Let me explain this further with this example here, this scenario. Let's say that I have this T flip-flop, and these are the waveform. Do you understand waveforms here? Yeah. So this is the clock. So it's 0, 1, 0, 1, 0, 1, 0, 1. And let's say that we have this input D. So D starts like this. So it's 0 for this time. Let's say that this is 5 nanoseconds. This is 10 nanoseconds. This is 15, and so on. So this starts like 0. It stays for 4 nanoseconds, and then it goes to 1, and stays 1 for this time, and then it goes back to 0 and stays 0. I'm just giving an example here, yeah? So if this is D. Now, if we ask you what will be the output if we have this scenario, and we say that this flip-flop here is positive edge triggered. Of course, you need to know, is it positive edge triggered? Is it negative edge triggered? Or is it pulse triggered? So you need to know the difference. And you need to know which flip-flop you have. Let's say in this example, we are working with positive edge trigger. So we need to look at these edges here. Those are the rising edges. And all what we need to do, and of course, assuming that Q starts with 0, so the initial value of Q is 0, so we start with 0. Now, at this rising edge, I need to check, here I have a rising edge, right? I need to check what is D. D is 1. Then this goes to 1 because of D. Do you understand? And then, when is the next rising edge? And then it will stay 1. I don't care about the falling edge. I don't care about this during this time. I don't care about the input D. Even if D has changes here, so if let's say that this is D, it changed here, I don't care. We just check D. So basically, to make it in simple words, we only check D on the rising edges, and that's it. And then we put Q is equal to D. I hope this is clear. Now, if I continue, now if I go to the next rising edge, D is 0. So this is why this goes to 0. So we update here at this Q follows D. We say Q follows D, right? And then the next rising edge, D is 0. So it stays 0. This is why we didn't change. It stays 0. The next rising edge, D is 0. So it stays 0, and so on. This is how it works. This is what we mean by rising edges or falling edges. So we don't update the output unless we have a rising edge. If this was falling edge, we don't update the output unless we have a falling edge. Pulse trigger is different story, and this is what I'm going to cover next. So let's say if I give you another scenario here. Let's say that this Q has changed here. Sorry, yes, this D has changed here, like that. Let's say that this is my input D. It was like that. It was 0, then 1, then 0, then 1, and so on. So here, as you can see, this is the next rising edge, it's 0. This is fine, it stays 0. The next rising edge is this one here. Now it's 1. In this example, this is 1. So Q should go to 1. Do you understand? So D type, it's very simple. So Q follows D. But now the question is, when does it follow it? It follows it when we have a rising edge. If your flip-flop is positive edge triggered, or it follows it when on the falling edges if your flip-flop is negative edge triggered. Now let's work with, if I ask you now the same example here, and assuming that this flip-flop that we have is negative edge triggered, do you think that will be the output waveform? So this is wrong now. If this is, it works with the negative edges, then this is wrong. We need to update it. We need to change. So we need to look for negative edges, and those are the negative edges. Negative edge here, or falling edge. Yeah, I'm using negative or falling, and we have one here. And now I need to update my, let's say we start with 0. Initial value is 0. This, it doesn't change. This is a rising edge here, so we don't care until I reach this edge here. This is the first falling edge. This is 1, so it needs to go to 1, right? And now we'll continue. Next edge is this one. In between, the flip-flop is 1, it stays 1. There is no change. Here, the new value is 0, so it goes to Q follows D. If D is 0, then it goes to 0. And this is why we get 0 here. And then as you can see, for the rest is 0, so it stays 0. And then again, it's 0, it stays 0. And so I will guess this. Do you see the previous one? This is the output Q, and this is the output Q if we work. So this is negative edges, and this is if we work with positive edges. Is this clear?
Yes, Doctor.
Okay, that's good. Now pulse triggered. So we'll give you again an example for the flip-flop. So what we mean by pulse triggered? With pulse triggered, we consider both edges. So remember, I told you when you go and buy a flip-flop, you need to specify which one you want. Do you want it as positive edge triggered? Do you want it as negative edge triggered? Or do you want it as pulse triggered? Now, if you go and buy one which is pulse triggered, and let's say I will do the same example here, it's the same scenario, but this one I consider it pulse triggered. So what is the difference between pulse triggered and only triggered by one edge? So the difference here, we consider both edges. So for the rising edge, we check D. But Q will not be updated here at this time. So we take the value of D. D is 1. And then we update it on the falling edge. So the Q do not change on the rising edge. On the rising edge is like we just read the inputs D. And then based on this value, we update the, so there is like a delay here, half clock cycle delay compared to this one. Do you see? It's the same form at the end, but it's delayed by half clock cycle. And then next rising edge, the is 0. We will update it here. We don't update it here like we did in the previous one, so we update it on the falling edge. And then the next rising edge is 0. We'll update it here. The next rising edge is 0. We will update it here. So the change will happen here. Is it clear? Do you understand the difference between the two? So they are very similar, but we work with the edges. Here, it will update immediately at the edge that we work with, either rising edge or falling edge. But here, we read the input. On one edge, we read the input, and on the other edge, we update the output based on what we read on the other edge. So it's not based on this value. Do you understand? So let's say if I change this one, this was like that. So it becomes 0 here. We are taking this value here. We are not taking the new value here. If as you can see here at this edge, now it's 0. I'm not putting here Q is equal to 0. Q is equal to this value that we read on the rising edge. And this is how it works, a flip-flop with rising edge. Oh, sorry, with the post-triggered flip-flop. So we used both rising edge and the falling edge. Is this clear? No answer? Is this clear? Okay. Now, so far we did SR and we did D. So now I'm going to move to JK. JK, we will find it only in flip-flops. So you cannot find the JK latch. So you can find only JK flip-flops. So JK, from the name, we have two inputs. One is called J and one is K. So this is different from the D flip-flop. The D flip-flop has only one input D plus the clock. Of course, when I say flip-flop, automatically there is a clock. I don't talk about it. Yeah, flip-flop, automatically there is a clock. Now, D, we have one input D. JK, we have two inputs. And this is a little bit similar to the SR. The JK is like you can think of the J and K as S and R. But the difference is here. For SR, when both of them are 1, it's not allowed. You cannot get it. But for JK, there is an output. So I will start with 0, 0. So if J is 0, and remember we have a clock. So again, this is a flip-flop. It works either with rising edge, it works either with or falling edge, or it could be pulse trigger. So we can have the three possibilities. And then if we have a rising, let's say we work with rising edges. So this table, we will consider it for rising edges. If we work with falling edges, then this table, we will consider it for falling edges. And that's it. I think it's very simple. Yeah, it's the same as what we did with the D flip-flop. Now, 0, 0 is no change. It's like the SR. So if I have 0, 0 here, and let's say I have a rising edge on the clock, if Q was 0, it stays 0. If Q was 1, it stays 1. So this is what we mean by no change. And this is what we mean by, so the next value for Q, Qn plus 1 is the same as the current one. So 0 stays 0, 1 stays 1. 0, 1 is a reset. So we force Q to be 0. 1, 0 is a set. We force Q to be 1. So far, it's very similar to the SR. The difference, as I said, is the last one. If J and K are both 1, 1, in this case, we will get the next Q is the opposite of the previous Q, of the current Q. So if current Q is 0, I will guess the next Q is 1. If the current Q is 1, I will guess the next Q 0. So it's Qn bar, the opposite. I hope this is clear. Right, let me give you an example with the JK before. I think I didn't put an example here, which I'll do it on the whiteboard before I show you how to use those components in simple circuits. Right, so I'm going to give you an example with JK. Let's say that I have a clock, this clock signal, and then I have let's say we will work with the rising edges. So just highlight the rising edges here. So those are the rising edges, yeah? Of course, what we do now will apply to falling edges, and it will apply as well to pulse trigger. And let's say that this is the J. J is like that. And then it goes to 0, for example. I'm just giving a scenario here, a simple example. And then we will have K has this form. What do you think will be the output? So this is clock, this is J, this is K, and then we need to find the output Q. And of course, you can do Q bar as well if you want, yeah? So we can do both. We always talk about Q, but so Q bar is the opposite of Q. Assuming that this, it starts with 0, so we start with 0. If this starts with 0, this means Q bar starts with 1, because it's the opposite, yeah? Now, I need to, now we are saying that the flip-flop that we have is positive edge trigger. So we will work with rising edges here. Those are the rising edges. So I'll just check what is J and K on those rising edges. And then we'll update the Q based on the truth table that we just showed you. So first rising edge, what is the value of J? And what is the value of K for this example? What is the value of J and what is the value of K? For this example here. Can someone answer the question? What is J and what is K? Answer. Do you understand what I'm doing here? Are you still connected?
Yes, doctor.
Yeah, so can you answer the question? Can someone answer the question? First rising edge. Where is the first rising edge? What is the value of J and what is the value of K?
The first rising edge for the value of J is the second one.
What is the value of J and what is the value of K? Do you understand those waveforms? Because I assume you know those waveforms. Yeah, because we in the lab you did them. Let's say, what is the first rising edge? Do you see the first rising edge? Can you tell me what is the first rising edge?
Which waveform, doctor?
Pardon?
For which waveform? The first one?
Yeah. So this is the first rising edge. This is the
yes.
first one, right? This
Yes.
is the second rising edge. Yeah, for the first rising edge, what is the value of J and what is the value of K?
J is
Here,
1, K is 0.
at this time here. What is
Yeah,
the...
J is 1, K is 0.
Yeah, J is 1, K is 0. J is 1, K is 0 here. So if J is 1 and K is 0, what should be Q? J is 1. Remember, we told you JK, it's similar to SR. So J is 1, this means it's a set. So Q was 0, starts with 0, and then we have 1, 0. It's a set. So what should be the value of Q?
1.
It should be set. Set is 1. So Q goes to 1 and stays 1 until the next rising edge. So it goes, sorry. So it's 1. It goes 1 and stays 1 until the next rising edge. The next rising edge, what is the value of J and K? At this time, what is the value of J and K? The second rising edge, what is the value of J and K? Oh, come on, you understand, you answered this question. So, and now you don't know how to answer this question at this time. What is the value of J and K?
J is 0, K is 1.
Why it takes so long, to answer those simple questions? J is 0, K is 1.
Doctor, it's because I'm in the university. There's some connection problem.
Oh, I mean, I'm not talking only to you. I'm talking to the whole class. Huh? So this comment is not to you. Yeah, thank you. You are answering. At least you are trying to answer. And so J is 0, K is 1. So 0, 1. This means it's a reset. If you check the truth table for J and K, when J is 0 and K is 0, it's a reset. This is in the slides, yeah? Reset, it means Q is 0. It goes to 0. And then we go until the next rising edge. So next rising edge, this is the next rising edge. J is 1, K is 1. What does it mean? 1, 1, it means that it's the opposite. We guess the opposite, Q bar. Do you remember? In the truth table, 1, 1, the next Q will be the opposite of the previous Q. This is the previous Q. Q is 0 here, right? So the next Q will be 1. So this is the previous one. This is the new one. Is the opposite. And then the next rising edge, it's 0, 0. 0, 0 is no change. J0, K0 is no change. So it stays 1. If it was 1, stays 1. If it was 0, stays 0. And then, as you can see, for all remaining cases, it's 0, 0. So it stays 1 and stays 1. Here, here, and that's it. And we'll continue until, if we have many cycles, you continue. Now, the Q bar is the opposite of this. I don't have to do this again. I will just do the opposite of the above. And that's it. This is Q bar. If I want to draw Q bar, usually we don't draw it, so because we know it's the opposite. Now let's change this one. If I change this signal, let's say that I have this scenario, and then I will have here 1 and stays 1, and then here I will have 1 as well and stays 1. So this is the next rising edge. So it was 1 until here. The next rising edge is here. Now it's 1, 1. 1, 1, we say it's the opposite. So it goes to 0 because it was 1. It goes to 0. It's the opposite. And then again, it's 1, 1 because it stays 1. It goes to the opposite. And then 1, it goes to the opposite. And we'll keep doing this. So it will get you, if we continue, we leave them all 1, we will get square wave, 0, 1, 0, 1 on the output, because we always keep getting the opposite of the previous value. I hope this is clear. We are just following the truth table, and of course you need to understand. Sorry, I need to stay in the, better to work with the, yeah. So I'm just using this truth table, and of course you need to know which edge you need to work. What I did the example that I gave you, it was with rising edge. I can use the same for falling edge, and we can do the same for pulse trigger. And we will do some examples, more examples in the tutorial. So this is for JK flip-flop. Now I will show you a simple circuit that we can get just with one flip-flop, either D flip-flop or JK flip-flop. So if I take a D flip-flop and I will connect this Q bar, as you can see it here, I will fed it back to D. We get on Q. So here, what you see here is what we get on Q. So basically, we have a clock signal. D is connected to Q bar. And so we'll start with this, and then we'll move to the JK. I can do the same with a JK flip-flop. Now, let's say that Q starts with 0. If Q starts with 0, this means Q bar is what? If Q starts with 0, this means Q bar is what? The value of Q bar. The starting value for Q bar. 1. Okay, good. So Q bar is the opposite of Q. Now, and remember, so Q bar is connected to D. And the value of Q should be equal to D if we have a rising edge. Again, I'm working with rising edges, yeah? If I don't mention which edge, it's the rising edge. The default one is the rising edge. So we are working with rising edges. Right, so Q starts with D. I think it's better to do it on the whiteboard because we'll have more space. Right, so this is what we are trying to do. We have D is connected to Q bar. This is D, and this is Q. And of course, we have the clock. So if I get just one flip-flop, and I will just do this connection. Now, if I have my this is my clock, and we say that Q starts with 0. So this is clock, CLK, and then we have Q starts with 0. I can add Q bar as well, so you can see it. And Q bar starts with 1. If Q is 0, Q bar is 1. So those are the rising edges. Right. And D is connected to Q bar. So at this time, the first rising edge, what is the value of D?
1.
First rising edge, what is the value of D?
The same as Q bar. I'm not sure if that's 0 or 1.
Yeah, it's the same as Q bar. And we said, let's say that the initial value for Q is 0 and the initial value for Q bar, it should be 1, right? If Q is 0, Q bar is 1. So it's 1. D is, I can put here, Q bar is equal to D in my circuit, right? So if D is 1, then Q should, at this time, at the rising edge, because we work with rising edges, this should go to 1. And please note that there is like a delay, you know, the transition, it's not like straight line. Yeah, there is time for it to go from 0 to 1. So it goes to 1. And at this time, at the same time, Q bar goes to 0, because Q bar is the opposite of Q. And this is how it will be updated. So at this time, here the next rising edge, D, which is equal to Q bar, is 0. So this will go to 0. And at the same time, this goes to 1. Because this is how a D flip-flop works. Q bar is the opposite of Q. And we will continue like that. So as you can see, we will get another square wave. Do you understand? Yeah. If we continue like that, we will get a square wave. As you can see, the period for this one is the double for this one, for the original clock. And we call this circuit is a clock divider. Because this Q then, I can use it as a clock with half of the frequency, because this is double. Period is double, which means the frequency is half. Yeah, for this Q. If I ask you what is the frequency for Q, is 1 over the period here, which will be double frequency of this clock. So I can use this Q to feed it into another circuit or another flip-flop where we need a clock that is double frequency of the original one, of this original clock. And you will see some examples later on, yeah? But for now, you need to understand how a simple flip-flop, by connecting D to Q bar, I will get this output. I will get another square wave, which has the double period of or half the frequency of the original clock. I hope this is clear. And this is what I presented here. So I just presented Q. I didn't put a Q bar, but you can, I think I showed you how to get it. I can do exactly the same with a JK flip-flop by just connecting J and K to VCC, or to have both of them 1. Because we know when J is 1 and K is 1, we will have the opposite, right? And then if I showed you this again, if I repeat this, what I did here, if I repeat it with JK, so now I'm going to use a JK flip-flop instead of it doesn't yeah. So now I'm going to use a JK flip-flop. So we'll have J and K connected to 1, J and K, and then we will have the clock CLK, and then we will have Q and Q bar. Right. And again, assuming that we will work with the rising edges, for the same applies to falling edges, yeah? And then if Q starts with 0, so this is Q. In this case, I don't need Q bar. So Q is 0. At this time, J and K is 1. We know that it's always 1, J and K. So the new value of Q will be the opposite of the previous one. So it was 0, it will become 1. And then it stays 1 until the next rising edge. And then the opposite. So it was 1, it will change to 0. And we'll keep doing this, opposite, 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 until I finish. So again, do you see it's the same output? So this is double of this one. So the signal that I get on Q is this signal, which is double the original clock. And we call this circuit clock divider. divide by 2. I can divide by 4 if I want by just connecting. So do you see this Q1? We did this, right? We did this in the previous slide. So we have this one. So I know this Q1 is half of this clock. So we'll get double period. Now I'm going to use this as the clock for the next one. So this Q2 will be double of this one, right? So the Q2 will be double of the Q1 because the Q1 is like the clock now for Q2 or the clock for the next flip-flop. And that's it. I think this is clear, right? If you understand the first one, I mean, I can divide, so this is dividing by 4. If I add another one here, I will divide by 8. If I add another one, I will divide by 16, and so on. And of course, I can do this with the flip-flop as I can do it with the JK. So I can add another JK here. So if I want to divide by 4, I will add Q here. So again, I will do 1 here, J and K, and then the clock will connect it here. And this Q, so this will be Q1, Q0, and this is Q1. This Q1 will be the double of this Q0. And I can repeat this or divide by 4, so I can generate different frequencies. Is this clear? So this is an example with D flip-flop. Of course, you can do it with a JK. You can mix. You can do here is first is a D flip-flop, and then you can use a JK here, and this will give you the same circuit. Is the same output. Right. In all the examples that I did, I said, okay, assume that Q starts with 0 and Q bar starts with 1, and so on. You will see that most of the flip-flops, they have extra inputs which we use to set or reset the outputs when we start. So usually when you power the system, or you have a big system, or you have a circuit, a sequential circuit, which includes flip-flops. When you power it up, I mean, the first thing that will happen is like we have a reset. So those signals, you just do just a quick one here. The beginning of when you power it on, you just put one on one of them to get it set or to get it reset, to start Q with 0 or 1, and then the circuit will start operating. So you may find only one. We call them the preset or clear inputs. So they are used to initially set or reset the flip-flop. You may have to set it, for example, to force it to start with 1, or you may have it, usually it's a reset. We always start with 0. So you may have it just to reset it, or you can have both. You can do whatever you want. You can start with 1, you can start with 0. And usually it's just one pulse just to get it to start with 0 or 1, and then that's it. The circuit will start operating. Is this clear? So now I will move to another circuit where we use flip-flops. We call it the shift register. Shift register is like to do the shift operation. So shift registers, they consist of flip-flops connected together. Like here, this is a clock divider. We have 2 flip-flops connected together. It's the same for shift registers. So we use either D flip-flops or we use JK flip-flops, and we connect them together to do shift register. So for example, if I want a 4-bit shift register, I will use 4 JK flip-flops or 4 D flip-flops. If I want an 8-bit, I will use 8 flip-flops, and so on. And then the way we connect them it will be different. So we can have different types. We can have 4 types of shift registers. We have the serial in, serial out shift register. We can have the serial in, parallel out. We can have the parallel in, parallel out, and we can have the parallel in, serial out. This, of course, will depend on inputs and outputs. So what do we mean by serial in, serial out? So I will just show you an example here. So as I told you, we will have flip-flops connected together. And flip-flops, you know, for example, if I take the D flip-flops, I have D, 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 and then we have Q, Q bar, Q, Q bar, Q, Q bar. So if I want a serial in, serial out shift register, this means I will get one input, single line. Serial in, it means just one line. Parallel, it means we have parallel multiple lines in the input. So it's like the input is, it goes to the first D, and then the rest will be used here, I mean, connected inside, and so on. And then we will have clock, of course, we will have clock for all of them. And usually they are clocked with the same clock signal. So clock is the, so what we mean by serial in, serial out is about the data, the D, not the clock. Clock, we always have it. And then serial out, this means this Q. We will have just one output, which usually we get it from the last one. Parallel in, serial in, parallel out. What does it mean? It means that we may get other Qs out like that. So we'll have multiple lines. So this is the difference between them. Serial in, which means it's one line. Parallel in, it means multiple lines. So I'll give you an example or 2 examples. And I will show you how do we get the waveforms, and then you will see what we mean by shift. This is a serial in, serial out shift register, 3-bit shift register. So 3 bits, we use 3 flip-flops. So do you see this is first one, first flip-flop, number 1, number 2, number 3. All of them, they have D, all of them, they have clock, all of them, they have Q. I didn't put Q bar, so we don't need to use Q bar here in this circuit. So it's there, we have Q bars, but we don't use them. We keep them unconnected. And this is the serial in. So this is my circuit. As you can see it, it's one circuit that has 3 flip-flops and 1 input. Of course, the clock is always there. In addition to the clock, we have the D as 1 input, which goes to the first flip-flop. And then internally, we connect the Qs to the other Ds, and then the output is just the final Q. If you observe this circuit, and let's say that I will get this D, I have this scenario, this input, D1. So we start with 1, and then stays 0. Of course, you can have different scenarios, there are different examples. Right, now I will, what do I get from the first Q? We said, and again, I didn't specify if this is rising edge or falling edge. This means all of them are rising edges, yeah, the default one. So if I take the first Q, Q1, we say Q follows D. So what is D? D, right, because I'm working with Q1. D1 is, it was 1. At this time, it's 1. And be careful, yeah, Q is 0, and then it goes to 1. At this time, Q is 0, sorry, Q1 is 0, and it goes to 1, because it follows D1. And then here it's 1, it goes to 0. But at this time, it's 1. At this time, it's 0, and so on. And then it stays 0 because D1 is 0, so it stays 0, it follows. Now, if I go to the next flip-flop, Q2, the D2 for the second flip-flop is the Q1. So we get it from, it's connected to Q1, and this is Q1. So Q1 here, at this time, it was 0. So it stays 0. And then at this time, it's 1. So it goes to 1. and then it's 0, and then it stays 0 because it's here it's 0. And then I will go to Q3, and the D3 for Q3 is connected to, oh sorry, the D3 for this third flip-flop is connected to Q2. So I can put here equal to D3, and this is equal to D1 or D2, sorry. Now D3 is here, and I want to find Q3. So again, I will work with the rising edge. So it's 0 here, it's 0 here at this point, and then it's 1 here, so it goes to 1. And then that's it. So as you can see, this 1 here, it starts at 1 here. It starts at 1 here in Q1, and then it's shifted every clock cycle. We get this one shifted. And then the next clock cycle gets it shifted. If I have a fourth flip-flop here, I will get it again shifted to the next clock cycle, the next clock cycle, yes, here. So we'll get it 1 here. So this one will be shifted by 1 clock cycle every clock cycle, so it goes to the next flip-flop. Now, this is another example with serial in, but I will guess it's, as you can see, it's exactly the same circuit. It's just taking the output together, and then we are going to use them together as an output, as a bus, 3 lines. So this we did it in the previous slide. Now, if we get them together, and this is how we represent, by the way, a bus. When we do simulation, this is how you will see it. So this means that this is not just a bit, so it's a bus. And here, this output here. Oh. So as you can see here, this includes Q1, Q2, and Q3 together here. So 3 outputs together as a bus. And then if you observe, this is from the previous slide, and now we have an extra output which we put them together. We have 1 0 0, 1 0 0, and then we have next slide is 0 1 0, 0 1 0, and then we have 0 0 1, 0 0 1, and then the rest is 0. As you can see, for all of them is 0, stays 0. So do you see this one here with parallel output? You can see it. You can see how this one is being shifted. And as you can see it, so if you consider the binary, this is 4, and then we get next is 2. So it's division, is dividing by 2. And then we get 1. So we keep dividing each clock cycle, we divide by 2. This is why, so shift registers can basically used as divider to divide by 2. Right. This is the last slide. I think the time is over. We will do please make sure before we go for the tutorial next session, inshallah, so it will be after vacation, that you revise what we covered today, and then how to, for example, design a flip-flop using VHDL. If you know how to design a flip-flop, you can design this circuit, right? Because you just use components. So if you know how to do the flip-flop, the rest is easy. You just use components and you connect them together. You can do any circuit you want later on, but it's very important to understand how they work. Right, so we'll stop here, and wish you a nice vacation, and we'll talk to you after the vacation, inshallah, if you don't have any question to ask. Right, Assalamu alaikum.